Welcome to The Explainer, everyone. I'm so glad you're here today because we are going to jump right in and take a journey straight down to the center of the Earth. We're going to unpack what might just be the absolute biggest untapped clean energy revolution sitting right beneath our feet. I'm talking about geothermal energy, the ultimate underdog of the energy world. You know, for decades, we've been looking up, right? We're looking at the sun, we're looking at the wind for our renewable energy. But what if the most powerful solution has literally been right below us this whole time, just waiting for the right tech to unlock it? Buckle up, because the story of how we're finally learning to harvest the heat of our own planet is absolutely fascinating.
So before we look forward, we kind of have to look down at where we've been. Take a look at this number, 12 kilometers. That is roughly a third of the way through the Earth's continental crust, and it is the absolute deepest that humans have ever managed to dig. Specifically, it's the depth of Russia's Kola borehole. Scientists started drilling this thing way back in 1970, just trying to study what the Earth was made of. But they hit incredibly hard rock, and it took them over 20 years just to reach that 12-kilometer mark. There were even these wild rumors going around that they were hearing voices down there, like they'd accidentally drilled into the depths of hell. Kind of creepy, right? Anyway, by the mid-90s, the funding totally dried up, the site was abandoned, and they just sealed it up.
Which obviously brings us to a massive, hanging question. So, what actually lies deeper? Just think about that for a second. We have never directly measured anything deeper than 12 kilometers. It is quite literally the final frontier. But here's what we do know for sure. We know the Earth's core is intensely hot. We know massive convection cells bring that heat up from the deep. And, most importantly, we know the Earth naturally produces enough geothermal heat in a single year to provide something like 10 times the amount of energy that the entire United States needs annually. The scale of that potential is just staggering.
All right, let's get into Section 1, the 12-kilometer limit.
Okay, let's dive into this. We've got the Kola borehole mapped out here against the sheer massive scale of the Earth's crust. Since the 1990s, that 12-kilometer record still completely stands. We simply haven't gone any further down. And while we're relying on coal, oil, and natural gas to cover 80% of our global energy demand, we're leaving this incredible 24/7 heat source almost entirely untapped. I mean, if you drill anywhere on Earth and just go deep enough, you're going to find hot rocks. And if you have hot rocks, you can turn that heat into electricity. But because of this drilling limit, we've basically been stuck.
Moving right along to Section 2, the geography of heat.
So right now, geothermal generates just 0.3% of electricity worldwide. It's a tiny, almost invisible little sliver. Why? Because historically, it's been considered completely impractical unless you happen to live in a few very lucky geographic hotspots. We're talking about places like Iceland, which brilliantly transformed its natural volcanic heat into incredible industrial output and a super high per capita income. Or take Kenya's Rift Valley, where an actual physical separation of the continental shelf makes the Earth's heat really accessible. In Kenya, nearly half of the whole country's electricity comes from tapping into hot steam just a few kilometers deep. But for the rest of the world, that heat is totally out of reach.
But here's why investors are absolutely desperate to scale this up. We've seen hundreds of billions of dollars poured into solar and wind, right? But they have one really critical flaw. They are variable. They're entirely at the whim of the weather. If it gets cloudy, solar drops off. If the air is still, the wind turbine stops spinning. Geothermal, on the other hand, gives us true baseload reliability. It's on 24 hours a day, 7 days a week, 365 days a year. It's clean, it's dependable, and it's good to go for another few billion years. It's the exact kind of constant, stable power that our modern electrical grids are practically begging for.
So the crucial point here is understanding why traditional geothermal has been geographically trapped for so long. To make a traditional plant work, you absolutely have to have these three strict geological conditions occurring naturally together. First, you obviously need heat. Second, you need a reservoir of underground water. And third, and this is the real deal breaker, you need a layer of porous rock. If the rock is just solid, fluid can't flow through it, which means you can't extract the heat. So outside of those rare places where the rocks are already hot, wet, and full of natural holes, geothermal has pretty much been a total non-starter.
Which brings us to a pretty wild plot twist. Section 3, Fracking for Clean Energy.
What if we didn't have to wait for nature to hand us those three perfect conditions on a silver platter? To completely redraw the map, the geothermal industry is borrowing heavily from a very surprising source, the oil and gas industry. The exact same tech that sparked the shale boom is what geothermal needs to break free. We are seeing a massive wave of highly skilled geophysicists, roughnecks, and drilling engineers migrating from giant oil companies like Shell and BHP straight into clean energy. One industry veteran summed it up perfectly. He said, "Oil and gas is kind of boring. Over here, we're starting a revolution." It turns out, The skills you use to pump fossil fuels are perfectly suited for pulling up clean underground heat.
And this brilliantly illustrates exactly how they're pulling it off. It's a process called Enhanced Geothermal Systems, or EGS. Companies like Fervo Energy are taking hydraulic fracturing, yes, fracking, and applying it to hot, solid rock. By injecting highly pressurized liquid down into the ground, they're creating brand new artificial gaps where literally none existed before. Essentially, they are turning the deep subsurface of the Earth into a giant artificial radiator. They pump cold water down an injection well, it flows through the new fractures, picks up all that intense heat, and shoots back up a production well to generate electricity at the surface.
The implication of this is just massive. Thanks to EGS, we've gone from needing 3 super rare, strict geological conditions down to just one thing: hot rocks. That's it. If you have hot rocks, you can provide the water yourself and you can create the porous fractures yourself. This completely changes the game. Suddenly, you don't need to be sitting on a geyser or a natural hot spring. The amount of land that can be developed for geothermal energy is expected to increase more than 100-fold. It means we could replicate this clean energy model in almost any country on Earth.
Let's look at another cool application. Section 4. The Earth as a battery. Because once you start artificially fracturing all this underground rock, you actually open up solutions to problems way beyond just generating baseline power. Another startup, Sage Geosystems, realized they could use these fracked underground cavities to solve the biggest headache for solar and wind: energy storage. Here's their method, and it's so clever. They drill into hard, non-permeable rock and fracture it to create space. Now, in places like California or Texas, solar panels often generate way more power than people actually need in the middle of the day. Sage takes that excess, precious clean energy and uses it to pump water into those underground fractures under immense pressure. The Earth essentially acts like a giant geological balloon. Later on, when the sun goes down and everyone turns on their TVs and grid demand spikes, they simply release it. The natural pressure of the Earth forces the water back up to turn a turbine. The Earth itself literally becomes the battery.
But it's not all smooth sailing, we have to be real here. Section 5. The Cost and Quake Dilemma.
Now, what's really interesting about this slide is the stark economic reality of it all. Just getting your foot in the door of the geothermal game requires a staggering amount of capital up front. Look at these costs. Drilling a single deep geothermal borehole can run you upwards of $90 million. Compare that to a single gas generator, which is usually $1 million or even less. Because of this absolutely massive initial price tag, these companies have to find cities willing to sign super long-term agreements. Investors need absolute confidence that power prices will be stable enough to provide reliable returns 20, 30, maybe even 50 years into the future, just to justify that initial $90 million bet.
And honestly, beyond just the money, there's an even bigger risk to the industry's reputation, and that is induced seismicity, earthquakes. Every energy source has its trade-offs, right? For geothermal, it's the fact that drilling and fracking can sometimes shake the ground. In 2017, an EGS project in Pohang, South Korea, used fracking techniques just a little too close to an active fault line. It ended up triggering a 5.5 magnitude earthquake, which was one of the largest to ever hit the country. Now, experts will quickly point out that events like the Pohang disaster are extremely rare, but even a single accident can deeply, deeply damage public trust. That's exactly why strict, constant underground monitoring is completely essential today. And companies are hyper-focused on proving they can operate safely without triggering any seismic events.
Let's look at the ultimate endgame here. Section 6. Vaporizing the deepest depths.
Even with those risks, the potential payoff is just too massive to ignore. Check out these projections. The International Energy Agency predicts that by 2050, total geothermal power capacity could explode from a measly 15 gigawatts today to over 800 gigawatts. That would cover up to 15% of the entire globe's electricity demand. The industry feels like it is standing right on the edge of the most dramatic growth curve it has ever seen. But to actually hit those gigantic numbers, we can't just rely on fracking relatively shallow rocks. We have to go deeper, a lot deeper.
Which naturally leads us to this huge question. What if we could drill literally anywhere on Earth? Right now, enhanced geothermal tops out at maybe 3 or 4 kilometers down. But what if we could reach 20 kilometers? If we can hit that depth, literally every single square inch of the world would have the natural geothermal potential of Iceland. You wouldn't need a volcano, you wouldn't need a rift valley. You'd just dig straight down in your own backyard to access endless, constant, extreme heat.
But remember the cola borehole we talked about? Conventional mechanical drill bits just get chewed up and destroyed when they hit that deep basement rock, like solid granite and basalt. They break, they wear out, and it takes decades. Well, a startup called Quaise Energy is taking a completely radical approach to this.
They are ditching conventional drill bits entirely, and they are turning to millimeter wave technology, basically highly targeted microwaves. These waves vibrate the dense rock, heat it up, melt it, and ultimately just vaporize it entirely. Their goal is absolutely mind-bending. They want to drill 10 kilometers deep, not in decades, but in just a few months.
And the craziest part? They are already testing this. In the lab, using what they jokingly refer to as a terrifying beam of death, they've shown they can melt a 4-inch hole right through a 2-inch thick block of solid basalt in just 90 seconds. Now, obviously, this technology is super experimental. It is completely untested out in the actual field. They might hit a snag, or it might fail entirely. But if it actually works, it fundamentally changes the entire business of energy. Heat suddenly becomes a service, available anywhere on the globe, completely severing our reliance on commoditized fossil fuels forever.
Which leaves us with this final thought. We live on a literal ball of energy. The heat beneath our feet is boundless, it is clean, and it is always on. As this incredible sci-fi level technology races forward, the only question left is, how deep are we willing to dig to unleash it? Thank you so much for joining me on this explainer today. I really hope this sparked your curiosity about the actual ground you're standing on right now. Keep questioning, keep learning, and I will catch you on the next one.